so I'd like to start by summarizing last class what you did with the graphs of motion for accelerating objects, and I want to extend that to talk about. So that was position graphs. I want to extend that to talk about velocity graphs as well. So to do this, I want to consider an object that is moving forward and slowing down. Slowing down. Okay, so if I do a position graph, and I want you to notice, I haven't really focused on this yet, but I want you to start making sure that you're labeling your axes correctly. So if I call this a position graph, again, we measure position as x. And why do we measure position as x? Well, if you remember, you can think about on an xy plane, right? So maybe don't draw this in your notes, but remember, if we think about this, we're thinking about an object that, if this is x and that's y, we're thinking about an object that's moving back and forth along the x-axis. That's why we're graphing the position. So even though this is what you usually think of as the y-axis, we're going to call it the position axis. This x stands for the position because I want to graph where the object is. So I want to graph the position across time. And you know, if you've got an object that's going forward, we know it's got to have a positive slope, and to slow down, I have to be getting flatter and flatter and flatter, right? So that is the graph of an object that's moving forward and slowing down. What if instead, well, let's talk about what we already know about this, right? We know that the slope of this graph, so the slope of a position time graph is going to be equal to rise over run. It always is. But the reason we can say that the slope is equal to the velocity is because the rise is a change in x, right? So if you pick 2 points and you measure the rise and you measure the rise is a change in x, and the run is a change in time. And that is the equation for velocity. That's why the slope of a position graph gives you velocity. Now, how does this graph show me I'm slowing down? It shows me I'm slowing down because the slope gets flatter and flatter. Okay, you know this. This is review. But now the question is, what if instead of graphing position, what if we graph velocity across time? Well, think about what's happening here. What does this graph look like? Well, what's my velocity at the beginning here? My velocity is fast, right? Because I'm steep here. So my velocity starts high and it gets flatter and flatter. So my velocity gets lower and lower. So I want to point something out here, right? These two graphs are showing the same motion. But a position graph tells me that I slow down because it gets flatter. A velocity graph tells me I get slower because the velocity, so the slope of x, this is kind of a graph of the slope of position, but the slope of x or the velocity value gets lower. So this tells me I get slower by becoming flatter. This tells me I get slower by getting closer and closer to 0, right? Now, what's the slope of a velocity time graph going to be? Well, let's think about this. If I have 2 points and I graph a rise over run, or in this case it would be a fall over run, but the slope, which is equal to rise over run, is equal to the rise, or in this case the fall, is a change in velocity, and the run is a change in time. Does that equation look familiar to you? It should, because that's the equation for acceleration. So what did we learn? The slope of a position graph gives you velocity, but the slope of an acceleration graph, the slope of a velocity graph gives you acceleration. I usually summarize this in something that I call the graphing roadmap. So if you start with x, which again is position, and you take the slope of it, you get v, which is velocity. And then if you take the velocity graph and you take the slope of that, then you're going to get acceleration. So the slope of a position graph gives you velocity. The slope of a velocity graph gives you acceleration. All right. I want to just summarize a few things real quick. So we did the slope. I want to figure out what else we can get from a position and a velocity graph. So I'm going to ask a couple questions. So direction. Which direction are you traveling? Remember how a position graph told us direction? Well, we know this is going forward. Why? Because it has a positive slope. So in a position graph, which I'm going to abbreviate an x, a position time, xt. A position time graph, the direction is given by the slope. So a positive slope would mean I'm going in the positive direction or forward. I say forward, but I really just mean the positive direction, right? Maybe I should say it this way. Positive slope means a positive direction. And a negative slope is going to mean a negative direction. Well, think about how would this velocity time graph tell me direction? Well, how do I know that this thing is going forward? I know this thing is going forward because it's positive, right? It's actually above the t-axis, right? So the way that I usually think about this is on a velocity time graph, if you're above the t-axis, that's going to mean you're going in the positive direction. And if you're below the t-axis, you're going to be going in the negative direction. You're going to see an example of this in a little bit. I'm going to ask you some questions on the Nearpod that sort of illustrates this. But so this is how you figure out direction on a position graph. This is how you figure out direction on a velocity graph. And then the other thing that I want to talk about is speed. And remember, speed is different than velocity. Speed is how fast I'm going. So how does a position graph tell us speed? Right? Well, remember, in a position graph, so in an xt graph, steeper means faster. So a steeper slope means faster, and a flatter slope means slower. Flat equals slower. All right. What does it mean in a velocity time graph? Well, let's look at this again. If I'm slowing down, right, how do I know I'm slowing down? I'm slowing down because my velocity is getting closer and closer to zero. So in other words, what I'm going to say is if you are farther from the t-axis, you're going faster. So up here I'm going faster because I'm far away from the t-axis. So if you're farther from the t-axis, you're going faster. If you're closer, I can't write on this, closer to t-axis, you're going slower. Sorry, I can't write on that paper on the edge. But farther from the t-axis, faster, closer to the t-axis, slower. Right? I'm fast up here, far from the t-axis. I'm slow down here, closer to the t-axis. All right. The next couple activities are going to help you practice this. By the way, I haven't decided yet if I'm making another video yet today. If I don't make another video today, just remember now so the acceleration part of your syllabus you can do, that's due on, I think I said Monday. And then you can now also do the graphs of motion part in your syllabus. Due date to be determined, but you can do those two parts now.